Okay, y'all. So we are moving to the second of our two database design techniques today. It's a technique called normalization, and it is a bottom-up design as opposed to a top-down design process. I think most people prefer ER diagrams, but normalization is actually a good check to apply to relations that you generate using ER diagrams, because with ER diagrams it's somewhat easy to end up with duplicated information in your relations, and you want to avoid duplication if at all possible. So it's almost like, you know how you write a paper, you write a first draft and then you go back and you write a second draft where you polish it. Think of maybe ER design as the first draft. It gives you a good thing to work with, and then normalization is kind of a good technique to apply to the second draft in order to refine and eliminate any data duplication that you might have left or come up with from the ER diagrams. So you might on your computer sometimes want to pull up the copy of the staff branch relation and the functional dependencies. They're on the handout today on page 407 and 413. I can't always show them. Okay, so normalization is essentially a mathematical algorithm for decomposing relations into logically related subsets based on functional dependencies between attributes. And we will get into that algorithm, but if you want to think of it in general terms, what we're trying to do is minimize redundancy. And let's see if I have a slide. No, I don't. Minimize redundancy, and the way that we're going to minimize redundancy is to essentially try to ensure that the only duplicated keys in our databases, duplicated attributes in our databases, are keys. We're going to try to make it so that all descriptive attributes appear in one and only one relation. So if you kind of want a summary of what normalization is ensuring, is normalization another way to think of it is normalization seeks to ensure that each descriptive attribute appears in no more than one relation. So the only duplication is with keys, okay? The only duplication, or the only duplicate attributes, are keys. Generally foreign keys and primary keys. In fact, the only duplicate keys really are foreign keys. Okay, that's what normalization is aiming for. So your only duplicate keys or duplicate attributes are foreign keys. So I will tell you, so what we're showing here is two entities conflated together, staff and branch. So we're showing all information about staff members, the branch that they work at, and the address. And what we're really doing here is conflating two entities, staff and branch. And I will tell you in advance that ER diagrams should allow you to avoid this situation. The point of ER diagrams is that you identify the entities and put them and separate them. But if you happen to design things from the bottom up to begin with, it's easy to come up with these kinds of tables because you're normally working with things like forms, and the forms will be structured like this, where they have a staff member, a name, a position. And so you'll simply copy all the information from the form into a table. And in that case, it is fairly easy to come up with tables that look like this, that essentially combine information about two different entities. Okay, so there's a few problems here. First of all, notice that branch address appears, this 22 Deer Road appears in multiple places. Okay, so let's say that branch 5 moves to a new location, and I only update this branch address, and I forget to update this branch address. That leads to inconsistency in our data. Okay, or I change the branch number here. Let's see. No, that's not a good example. What's another example? I think that's the only example I have here. Okay, so that's an example of what we call an update anomaly. If I change the branch address in one place, I have to change it in all these other places as well. Or if I change the branch at 163 Main Street, I'm going to have to change all instances of that. If I forget, I get what is called an update anomaly. Okay? As another example, let's say that I'm building a new branch at 1500 Nayland Avenue, Knoxville, Tennessee, and I want to insert that into this relation. But I can't do it because let's say that the primary key is the staff number. So the problem is I can't insert a tuple into a relation if the primary key is null. So I actually would not be allowed to insert a new branch into this relation unless that branch has a staff member associated with it, and I may not want that. Okay? That's called an insertion anomaly, the inability to insert certain information unless other information is available. And then the third type of anomaly we worry about is something called a delete anomaly. So if I delete Mary Howe from this line right here, Mary Howe, you'll notice that she is the only person currently in the database who works at branch B7. So if I delete Mary's tuple from this relation, I also lose the information that branch B7 is located at 16 Argyle Street. I can't find that anymore in the database. It's gone. That's called a deletion anomaly. It means that when I delete information, I may inadvertently lose other information that I didn't intend to lose. Okay? And it is the case, in fact, that every insert anomaly that can happen has a corresponding or symmetric delete anomaly. Okay, because if I can't enter a branch unless I have some staff member's information, what that means that if I get down to a single tuple with that staff and then delete it, I will delete that branch information. So for every insert anomaly, there is a symmetric or corresponding delete anomaly. Okay, so I'm trying to avoid these three types of anomalies when I do normalization. Okay, so these are the three, let's see. The other type of update anomaly here is if I change the branch for John White. Say I move John White to branch B7. Let's say I forget to update his branch address. Then I have data inconsistency. So there's two types of potential update anomalies in this relation. One is I move someone to a new branch and I forget to change their branch address. The second update anomaly is that the branch moves to a new location and I forget to update all the locations. So there's two types of anomalies that can appear in that relation. Okay? So update, insert, delete. We're trying to avoid those three types of anomalies. Okay? So again, the way we're going to try to do that is to decompose our relations into smaller relations that don't necessarily have this duplication. And there's two important properties that we're going to have to maintain when we do it. One is called the lossless join. It means that when we decompose a relation A, so actually let me show that. So lossless join means that when we decompose A into B and C, it must be the case that B joined, with C is equal to A. That's the lossless join property. Okay, and the way we accomplish that is with foreign keys. Basically, we need to move the same set of keys or attributes into B and C. So B and C will match, will have a common set of attributes which are foreign keys. Now in practice what happens, one of B or C is a slimmed down version of A. So it's really not A being split into B and C. It's really A becoming A, say, prime, and B, meaning A is a slimmed down version of A. I'm sorry, A becomes a slimmed down version, and some attributes leave to go to B. So whatever is the primary, so what really happens is whatever is A's primary key is copied to B, along with some other attributes, or part of, I should say, actually, as we'll see, part of A's primary key is copied to B, typically. So that's going to give us this lossless join. Questions about that? Okay. The second thing that's going to happen, there we go. My mouse, so this pen was sitting on the thing and that pinned my cursor. Okay. So the second thing is that we want to enforce constraints on the original relation by ensuring that the same constraint is enforced on one of the smaller relations. So, as an example, back here, we can kind of see that the branch number determines the branch address. So, should we move the branch number to some other relation, the branch address has to come with it because we need to preserve that constraint that the branch number determines the branch address. Or similarly, if we were to move staff number to a different relation, well, staff number determines staff name, position, and salary. So we'd make sure that that information all went as a package. So if we have one attribute that determines some other attributes, if we move the defining attribute like staff number, we have to move all of its dependent attributes with it. So that's what we are saying here with the dependency preservation property. It's essentially saying that when we move some key or independent attribute, we have to move all of its dependent attributes with it. Okay, so those are the two important properties that we are seeking to maintain. And the way that we crystallize this dependency preservation is in the form of functional dependencies. So a functional dependency is a relationship among attributes, and it's essentially the kind that you're familiar with from 311. It means that for each value of the left-hand side, so basically what we have if we are going to say that A determines B, it means that for each instance of A, we get a unique value for B. Okay, so no matter, it's a one-to-one mapping. Now you could have this. You're allowed to have f of A2 also equals B1. Okay, but you can't ever have, for each value of A, there is only one value associated with it. Here, you can see the opposite is not true. F of B1 can equal A1 or A2. So that's not a unique value for B1. So it doesn't go the other way. Okay, so for example, if this is position, we might say that the position of Fred equals student, and the position of Mary is also equals student. That's fine. It's not okay, for example, to say that the position of Fred could be a student or a professor. So it's a one-to-one mapping from the left side to the right side. Okay, and that's what is shown in this diagram. So we have a functional dependency that staff number determines the person's position. So for each staff number, we will get exactly one position, but the converse is not necessarily true. For manager, that could actually lead to two different staff numbers. So a position does not determine the staff number, but the staff number uniquely determines the position. Okay, so an important term is the determinant. It refers to the attribute or group of attributes on the left side of the arrow. So get familiar with that term, determinant. It is the left-hand side attributes in a functional dependency. Okay, and another important thing about functional dependencies, you can't necessarily infer them from the example data. You have to make sure that it is a fundamental business constraint. So I might give you a directory, and in it, it appears that all staff names are unique. But that's a pretty bad assumption. In a large company, there's a good chance that there will be at least 2 employees that have the same first and last name. So you could easily, by just looking at some sample data that contains unique names, decide that staff name uniquely determines staff number. before you go and make that assumption, you better verify it. Okay? So that's the very important thing out in the real world, or even possibly on the homework assignments, is that if something looks true from the concrete data, that you actually verify it is really true, not, just a fluke that the example data wasn't as complete as it might be. Okay, remember back to the hotel data I gave you? I think the hotel data I gave you omitted double bookings of both rooms and guests, and that's information you had to add to your example data. So if you'd simply looked at my example data for hotels, you might have assumed that double bookings were impossible and having 2 rooms double booked was impossible, which in fact it was meant to be, but it's something you need to verify. Okay? It's not something that's necessarily true. So at any rate, you have to make sure that functional dependencies that appear in the concrete data is really, in fact, true. Okay, we also, just like remember super keys and candidate keys, super keys uniquely identified all tuples in a relation, but they weren't necessarily minimal. And what was a minimal superkey? Do you remember? That had the minimum or irreducible set of attributes that uniquely identified a set of tuples in a relation. You'll need to know it for the exam. Candidate keys. So candidate keys were superkeys that were irreducible. We have the same thing here, which is something called a full functional dependency versus a partial functional dependency. A full functional dependency has the minimum number of attributes necessary to maintain the functional dependency. A partial dependency has extraneous attributes on the left-hand side. So here, staff number and staff name determine a branch number, and that is true, but is a partial dependency because staff name is unnecessary. By itself, staff number determines branch number. So the dependency staff number determines branch number is a full functional dependency. This one that you see here is a partial functional dependency because staff name is unnecessary. Okay, so full functional dependencies are irreducible. Remove any attribute from the determinant, it no longer uniquely determines the right-hand side attributes. Partial dependencies are reducible. You may remove one or more attributes from a partial dependency and still have your left-hand side uniquely determining the right-hand side. Okay, so this is kind of just a summary of what a functional dependency must be. It's one-to-one, holds for all times, and is the minimum number of attributes in the determinant that's required in order to uphold the functional dependency. So questions about functional dependencies. Okay. So there's a type of functional dependency called a transitive dependency. Okay. So if A determines B and B determines C, then there is a transitive dependency from A to C. Okay, so as an example, we might say that the let's see. Let's come back here. So we have staff number uniquely determines a branch number. So that is a functional dependency. We also know that the branch number determines the branch address. So there is a transitive dependency that staff number determines the branch address. Okay, this is a transitive dependency. We do not represent transitive dependencies explicitly in our database if we can avoid it. Okay, so if we can avoid it, if possible, we avoid representing transitive dependencies in the database. Now there's an exception. What is the exception? You don't have to remember it, but it is useful. When they're needed to fix a chasm trap. You may remember that we had back in the ER diagram something where a branch number determined a wasn't that way. It was that way. A staff number and a property was managed by a staff. But the problem was that sometimes a property was not managed by any staff. So there was a 0 here in the relationship, and it caused a chasm trap. And the way we fixed it was we created this dependency that we had a branch number associated with a property number. So in that case, we were fixing a chasm trap by explicitly representing the transitive dependency between a branch number and a property number. But we try to avoid that if at all possible. So in general, we do not explicitly represent transitive dependencies in the database, with the exception of when we have to do it in order to fix a chasm trap. Okay. And I just went through this example, so we don't have to do it again. Okay, so now we can do a little exercise and try to identify the set of functional dependencies in the staff-branch relation. And one assumption we're going to make is that the position that is held and the branch determine a member's salary. So if we go way back to slide 6, we are going to assume that if there was 2 people at the same branch, they would have the same salary. So I know that we don't, I think, see that here. I don't think there's ever someone. But let's say that we had another person here who was also an assistant at branch 3. They would also have to have a salary of $12,000. So what I'd like y'all to do, take a moment, see if you can't work out what are the functional dependencies for this particular relation. All of them. Okay? So take a moment. I'll give you about 4 or 5 minutes. You can talk to a neighbor. It might help to scribble it down on a piece of paper. There are, I can give you a hint. There's 1, 2, 3, 4. There are 4 functional dependencies here. Pardon? No, there's like, it's, some of them, remember, you can have multiple columns on the left-hand side. So there's going to be more than, so at least one of the functional dependencies will have more than one. Okay, I'm just going to check something real quick, make sure I've given you the right information, that there are 4 functional dependencies there. Nope, there's 5, sorry. There are 5 functional dependencies. See if you can find them all. And as a further hint, 3 of them have a single attribute on the left-hand side, and 2 of them have 2 attributes on the left-hand side. Okay, I am going to go over the solutions. So here they are. Here are the 5. So the staff number uniquely determines a staff member's name, position, salary, and branch number. Branch number uniquely determines the branch address. Now, none of you asked, but it seems pretty clear that a branch address uniquely determines a branch number. I told you that was the 4th and 5th ones come from here. Assume that the position and branch determine a staff member's salary. So branch number and position determine salary. But since the branch address also uniquely determines the branch, we also have that the branch address and the position determine the salary. Okay. It's that 5th one that got me. I forgot about the fact that the branch address, since it also uniquely determined the branch, was involved in a functional dependency. Okay. These are the kind of questions I would ask you on an exam. Okay, I would give you a relation like that, some example data, some assumptions, and it's true on the homework too, ask you to derive the functional dependencies. Okay, so we are going to use these functional dependencies to determine our primary keys. Okay, I think you have enough practice already that I'm going to kind of skip that part because I think it's pretty easy once you have the functional dependencies to figure out what is the going to be your primary keys in the relation. Okay, and the last one is staff number. Staff number determines everything else. Okay. Now, you may also remember have candidate keys. So just going back for the branch relation, we know that the branch number determines the branch address. Eventually, it's going to be the case that we're going to have a branch relation and the branch address could be the primary key too, because it uniquely determines the branch number. Now, that's not true for our relation. The relation we have is essentially a directory relation of all staff. The branch number is not unique in that one. It's not a primary key. The only primary key is staff number in our directory relation that we have. That's the only thing that's uniquely identifying each tuple. Okay, so we've done all the groundwork, given you the basic concepts. Now, remember at the outset I said normalization is an algorithm for decomposing relations into subgroupings based on logically related attributes. So, the logically related attributes are the ones related by functional dependencies. So, I can now reword what I told you at the beginning to be normalization is a way of decomposing a relation into subrelations based on functional dependencies. And it typically is, for this course, a 2-step process. However, conceptually, it could be multiple steps. So, again, the mathematicians have gotten busy and come up with all kinds of normal forms. BCNF is called Boyce-Codd normal form after its creators. 4th and 5th normal forms have been articulated as well as higher normal forms. In practice, it is generally good enough to get your relations into 3rd normal form, and that's what we're going to do in this course. We're not going to worry about the higher normal forms. We're only going to worry about getting into 3rd normal form. Now, as you get higher up, you get less and less redundancy. So the higher the normal form, the less the redundancy that you have in your relation. So it's going to turn out that first and second normal forms still have some redundancies that could lead to update, insert, and delete anomalies. But by the time we get to third normal form, it's actually tends to be pretty good as far as having eliminated most of whatever anomalies you could get. And so that's where we stop. So there actually is something called unnormalized form, which I pretty much never deal with. But if you have something like a form and you're just creating a table, a sample table from a form, you could end up with repeating rows, or repeating columns for things like phone numbers. If there are multiple phone numbers, or let's say you were looking at leases and you come up for each customer or each property owner, you might come up with multiple leases. That would be considered unnormalized form. The reason is because you have either repeating rows or you have multi-valued attributes, both of which aren't legal in a relation. So what you have to do to get to first normal form is get to a table in which each row and column contains exactly one value. So you eliminate your multi-valued attributes, typically by pushing them off into another relation. And if you have repeating rows, it's generally the same thing. It turns out that they probably should be in another relation. So that's essentially what you are up to. So repeating rows essentially means you have a relationship, like a lease relationship. And you normally have to, as I say, find a way to separate those into two separate tables. So in first normal form, you have a table, no repeating rows, because duplicate rows are not legal, and you have only one attribute value per column. Okay, now this is pretty easy, so we're not even going to bother covering it. So that's staff directory, that staff branch relation I gave you, that was in first normal form. So in this course, I will give you all the relations I give you that need to be normalized will be in first normal form. So we pick it up from there, and as you could see, first normal form had a problem. And that problem was essentially that it allowed entities to appear in the same relation. So actually, I'm going to add something here, which says that first normal form, it allows two or more entities to be conflated in the same relation. Conflated means to be juxtaposed or combined together. If you haven't seen the definition for conflated. Okay, so it allows two or more entities to be conflated in the same relation. That's not good. Okay, we want each entity in its own relation. So second normal form, whatever. Whatever. Okay, second normal form, I have a conceptual definition, but that's actually a little too, let's see, I'm going to say high-level definition, or actually a conceptual definition. Conceptual definition is every entity is in its own relation. Let me turn that into blue somehow. Where's the color? Is that the color? Nope. How about you? Is that the color? Nope. How about undo? Oh well, you get the point. Every entity is in its own relation. Okay, more technical definition. A relation that is in first normal form and every non-primary key attribute is fully functionally dependent on the primary key attribute. That's a mouthful, right? That's why I gave you the conceptual definition first. So essentially, when we go from first to second normal form, it's really an exercise in making sure that we, actually no. That's third normal form. Sorry. I did not get that right. This happens when you get a spur of the moment thought. That's actually third normal form. So I will delete that out from your notes. Let's call this conceptual still. Guess I don't have the brain insight yet to give you a good conceptual definition for second normal form. Third normal form will have every entity in a separate relation. But second normal form means that we remove all partial dependencies on the primary key, and we're going to move them to their own relations. So it turns out that the staff branch relation is already in second normal form. And the reason that it is already in normal form is that if you have only one attribute in the primary key, you can't have partial dependencies. It's only if you have multiple attributes in the primary key that you might end up with a problem. So as an example, here we have lease information. So this would presumably be taken from a lease form. Pretty reasonable to create a table from a lease form. And that form has some information for the client, the property number, the name of the client, the property address, when the lease starts, when the lease finishes, what's the rent, who owns the property, and what the owner name is. This is all standard information for a lease. So you copy this information from a lease. Again, in the real world, this would happen. You would have a lease form. And the way you normally get your initial information is off of forms. And what do forms do? Forms show relationships between entities. So there's a good chance when you copy the information off of the form, you're going to conflate information from different entities, which is what you're going to do here. You have a client, you have a property, and you have an owner. So you have three entities conflated in this one form. So let's say you actually create this table. Now we want to normalize the table by converting it to third normal form. So we have to find the functional dependencies first. This is a little harder. But so here, if it doesn't have an arrow, it's a left-hand side attribute. If it does have an arrow, it's a right-hand side attribute. So here, the client number and the property number uniquely determine when the lease starts and finishes. And I'm assuming no client leases the same property twice. If I did, I would have to add the starting date of the lease to the primary key or to the left-hand side. But I'm assuming in this case that knowing a client and knowing the property, that uniquely determines when the lease started and when it ended. Now you'll note that I don't have additional stuff in here, like I don't say that the client number and the property number determine the client name. But that is true. But the reason I don't have it is because that would be what? If I had the client, what uniquely determines the client name? You can see it here. The client number uniquely determines client name. So the problem is if in this top dependency I had an arrow up to client name, it would no longer be a full functional dependency. We only show full functional dependencies. If I had an arrow in this functional dependency, this first one up to client name, it would be a partial functional dependency. And the reason is client number by itself uniquely determines client name. And we said full functional dependencies had to be irreducible. So we don't include in a functional dependency attributes that are determined by a subset of the left-hand side attributes. So in this case, client name is determined by client number, property address is determined by property number, rent is determined by property number, owner number and owner name are determined by property number, but those are not, the problem is they're determined by a subset of the primary key. So here you see client number determines client name, then property number determines the other four attributes. Okay, and we also have that owner number determines owner name. Now, I wouldn't bust your chops for omitting this arrow here. Okay, why is this arrow perhaps not necessary based on what I've already told you? This arrow right here. I'm sorry, this arrow. I take it back. This is the arrow that really is not necessary. Very good, because I can actually obtain the owner name from the owner number. I said that if at all possible, we avoid explicitly representing transitive dependencies. This one right here is a transitive dependency. So I would actually probably prefer that you not show this particular dependency because it is transitive. It's really determined by owner number determining owner name. Okay, but I wouldn't worry too much if you did. Now, there are two alternative candidate keys here. Okay, and that is the client, and the start of the lease uniquely determines a bunch of attributes because I said a client can only have one lease at a time. Therefore, if a client can only have one lease at a time, that should determine where the client currently stays, the address, the rent finish, and all that other stuff. So again, I'm showing transitive dependencies here. That's fine. And the other one, a property can only, if we assume that a property can only be rented to one person at a time, which might not be true. As you all know who have roommates, it may be that more than one name appears on the lease. So that would be something you would have to look into is, can only one person's name appear on the lease? Or can multiple people's name appear on the lease? Here, I'm assuming that only one person's name appears on the lease. Therefore, the property number and when its lease date starts determines uniquely. some other stuff, the who's staying there basically. Now, there are other functional dependencies here that I did not show you, that I would expect you to show me on a test or a homework assignment. Okay, based on what I just told you, there are two other functional dependencies missing from this slide. What are they? Look at the bottom, not at the top. Those two at the bottom should give you some ideas. As a hint, think back to the hotel when we talked about that and what were candidate keys, like say for booking. And yes, very good. So just as the starting date of the lease determines the lease, the ending date too. You can't overlap them. So it is also the case that the client number and the finishing date of the lease should uniquely determine all of these attributes. And the same thing here, a property number and its finishing date, since it can't be presumably leased to two people at the same time, not only should the start date be uniquely identifying, so should the finish date. So I could add two additional candidate keys, one with client number and rent finish, one with property number and rent finish. So you got to be careful in these things because it's very easy for things like dates or addresses to lead to functional dependencies that you may not anticipate. Okay? Questions about that? Okay. So when I go from first to second normal form, what I'm going to do is I am going to remove what are called partial dependencies. And that is a partial dependency in this case is a dependency that where the left-hand side is a subset of the primary key. So when we go from first to second normal form, we're going to eliminate partial dependencies on the primary key. So if we come back here, the primary key is client number and property number. We have two dependencies that are partial. Client number is a subset of the primary key, and property number is a subset. So we're going to remove the attributes associated with those two partial dependencies and put them in separate relations. Remember, we have to have a lossless join. The way we preserve a lossless join is we retain in the original relation the left-hand side attribute. So property number will stay in the original relation. In the new relation, we place all attributes in that functional dependency that we are moving out. So in this case, we're moving the attributes associated with this property number dependency into their own relation. We move all of them out of the original relation and into the new relation. So if the original relation was lease, we now are moving the property information out into its own relation. And we're also going to be moving the client information out into its own relation. So again, we copied out, this is the foreign key, so we're maintaining the lossless join property. So the way we maintain the lossless join property is by copying out the left-hand side. The way we maintain our dependency preservation is by copying all the attributes in the dependency to the new relation. So going way, way back to the beginning of the lecture, way, way back, wow, we have to preserve these two properties. So when we go from first normal form to second normal form, the way we preserve the lossless join is through the left-hand side. The left-hand side stays in both the original relation and in the decomposed relation. The way we do the dependency preservation is we move or copy, actually, we move all right-hand side attributes, and we don't move the left-hand. We copy the left-hand side and move all right-hand attributes to a new relation. So all attributes in the functional dependency end up in the new relation. So that's how we do the dependency preservation. Okay, so in this case, we end up with two new relations, client and property owner. So that got us two of our entities were removed from here, and in fact, this one is looking pretty good now, this lease, but we still have an issue. We still have owner information sitting in property owner. So we still haven't gotten every entity into its own relation. Okay? So that is what we do when we take second normal form to third normal form. In third normal form, we're going to eliminate any transitive dependencies. So any transitive dependencies we have in our second normal form relation are going to be moved into their own relation. So here, owner number determines owner name. So to move from second to third normal form, we move the attributes associated with that transitive dependency to their own one and keep the left-hand side up here in property for rent. Now, in third normal form, we in fact have all of our entities in separate relations. Okay, so essentially, I'm going to go back now to third normal form, and I am now going to say in third normal form, okay, conceptually, every entity is in its own relation. Of course, then I have to move everything around. So I'm not going to do that now. But what I'm saying, every entity is in its own relation. So that's third normal form. Okay, so, and again, the way we do that, we identify the transitive dependencies, move the attributes associated with the transitive dependencies into their own relation, and we are done. Now, the primary key that we choose will determine what is in second and third normal form. In this class, you will end up with the same set of third normal form relations. But if I had changed my primary key from client property number to client number and rent start, I would get a different set of second normal form relations. Okay, and the reason for that is now when I do the decomposition, if it's client number and rent start, what dependencies will I use to go to second normal form? So if this is my key that I use as the primary key, what dependencies will I use to go to second normal form? Remember, to go to second normal form, it's going to be a dependency whose left-hand side attributes are a subset of the primary key. I have 50 eyes on this. Surely someone sees a dependency where the left-hand side is a subset of these two attributes. Client number and rent start are my new primary keys. How about this one? Client number determines client name. Client number is a subset of client number and rent start. So if I chose this key, if I chose client number and rent start to be my primary key, then the only dependency I would use to go to second normal form is client number determines client name. And my transitive dependencies that I would use to go from second normal form to third normal form would become the owner number goes to owner name, and I would also have property number going to property address, rent, and owner number. So in that case, both property number going and owner number would become transitive dependencies. So it is important when you're going from first to second normal form and second to third normal form that you know what primary key you're using, because your second normal form relations will be different depending on which primary key you choose. Your third normal form relations will be the same, but your second normal form relations could be different. Okay, you kind of see that? Okay. So, as a summary, we use partial dependencies to convert first normal form to second normal form. We use transitive dependencies to convert second normal form to third normal form, and there is a third type of dependency, so-called candidate key dependencies, and they are not used in the normalization process. Okay? And once the third normal form is reached, the original relation you were using should only have the attributes that are fully functionally dependent on the primary key. Okay, so just going back here for a moment, you'll notice we didn't use either of these dependencies when decomposing here. But if you look at the final set of relations, we still have to make sure that the client number and the start of the rent is going to determine the remaining things. So in the final set of relations, final set of relations, one of them is rental, and it is the case that client number and rent start are there together, determining property number and rent finish. It is also the case that property number and rent start are still there together, determining client number and rent finish. So in fact, these dependencies right here have been preserved. And you might say, no, they haven't, Brad. I don't see, you said that client number and rent start determined property address right there, and I don't see it here. Where is property address? It's a transitive dependency. So technically, I should never have represented this one right here, nor these three, because these four, 1, 2, 3, and 4, they all depend on property number. So technically, this candidate key here should have only had the arrow to property number and to, I think that's it actually, rent finish, because everything else was a transitive dependency. Okay, final thing. In this course, we are only going to worry about what is called primary key, second normal form, and third normal form. But there are two more general definitions of second and third normal form. So the more general definition says that not only that when you have your relations in second normal form, not only do your descriptive attributes not depend on any partial dependency in the primary key, but they also don't depend on any partial dependencies in any candidate key. And the same thing for third normal form is that you can't have anything that is transitively dependent on any candidate key, not just the primary key. So as an example, back here, if I chose as a candidate key client number and rent start, the only thing that depends on the primary key is client number goes to client name. But if you look at the alternate candidate key, you see that in addition, in the alternate candidate key, property number determines some things, and therefore when you went from first normal form to second normal form, not only would you use this dependency, but using generalized second normal form, you would also use this dependency. And the reason is because this dependency is a partial dependency in both this candidate key and in this candidate key. So in that case, you would have used both of these dependencies to go to generalized second normal form. Again, we're not going to use generalized second and third normal form in this class. We're only going to use primary key normal form, but that was a nice example of the difference between the two. Okay? So with that, I will let you go, turn you loose on the homework. Very important announcement that I forgot to make at the outset. I will not be here next week, so class is canceled next week. However, you are still responsible for the material. And I have 2 excellent lectures that I already did. So if you go to lecture notes and you look at 211, there is lecture 2. And for 213, there is lecture 1. You are responsible for those lectures. I will post all this information on Piazza. You are also responsible for the quizzes associated with 211 and 213. So don't forget that even though class is canceled, watch those videotaped lectures and do the quizzes. I will post that information to Piazza.